Lucky Group 13.
I hope.
Okay.
Look at it.
We're not supposed to know on a Friday, we're safe.
There you go. Good
That's
attitude.
really blinding.
It's very great.
Okay, so we know he's not.
Not
And,
I've got a laser pointer, if you need a laser pointer.
Yeah,
yeah, he actually won't be attending today.
Are any of you guys still looking for a job?
No, we all
Actually,
unfortunately
Oh,
no.
okay, because I have some, one of my students in grad classes, they're hiring a couple people, so.
Where at?
It is, Applied Research Associates, it requires, security clearance, citizens,
I think we're all set on
Yeah,
that.
Does anyone want a laser pointer? I'm not gonna need, like, we can swap this around forever for
I don't need it for first.
And you said pretty much Avelino's iffy kind of thing?
Yes, he'll either be late, well, if he shows up at all, he'll be late.
Okay, in that case, we're not going to wait for him. Again, thank you to all of our evaluators here. We appreciate you taking time out of your schedule. I always like to say that. Make sure that you know how much we appreciate it when the students ask you to participate, that when you say yes, again, it's very appreciated. This is spring semester, so you have two forms. The first form is the form with the 0 to 10 or 0 to 15. That's actually used to calculate their final grade. The second form is the ABEC form, which is the familiar A through K style of questions, which are very difficult to answer with limited interaction with the groups. I know Patrick interacts often with them as well as myself, but if you are able to answer those questions, we appreciate it. If not, just check the not applicable box. I need to rename that to insufficient data box, which is how I interpret it when I enter the data. Having said all that stuff, we'll let Group 13 begin.
All right, well, good afternoon. As Dr. Ritchie said, thank you for coming out and taking time out of your busy schedules to come see our presentation. I do have a couple extra copies of our conference paper if anyone would like one. Well, as our PowerPoint states, we are Group 13, and we are the Aerial Intruder Removal System for tracking and rendering ineffective knavish enemies, or airstrike for short. I am Scott Greenwald. I am the electrical engineer in the group.
I'm Andrew Kirk. I'm photonic science and engineer in the group.
I'm Kevin Chow, I'm a computer engineer. I'm Christopher Walls, I'm also a computer engineer.
So what is airstrike? When we sat down after forming our group and trying to figure out what we wanted to do for our senior design project, we put all of our interests in just out on the table to see what we had. And currently at that time, or in the past, all four of us had worked at Lockheed Martin as for an internship, and all four of us actually have jobs there, and that's where we would be working. And after we put all of our interests out there, being mine was in circuit design, Andrew's was in optics, Kevin's was in networking, and Chris's is in image detection, the idea of a tracking system came out very easily based on our past at Lockheed and our interests as well. So that is what airstrike is. So our goals and objects of this project was to build a fully autonomous surface-to-air turret system that uses a directed energy system to neutralize our targets. It's basically a targeting system that'll be able to shoot a laser at any different colored balloon. And we wanted to make this as realistic as possible because this is the industry that we will be going into after graduation. So I really wanted to focus on safety, maintainability, and precision. That way our system is fully portable, being autonomous, and safe as well for any users that use it. As you can see, here's just a list of some of our requirements. I'll let you look through them really quickly, but take note of two of them. The first being that we wanted a minimum range of 10 feet for tracking, and that we wanted a minimum field of view of 70 degrees as well. So before we get into the technical aspects of our project, here's a quick block diagram of our total system. As you can see, our directed energy system, our gimbal, and our Pixie camera, which is the camera that we use on board, are all directly connected to our MCU circuit board, which is then able to be either powered from a separate circuit board that we have or a USB port to any outlet or computer as well. So I will pass it over to Kevin.
Okay, so for our microcontroller, we went with the CC3200 because it had all the required interfaces to communicate with our peripherals, which are one Pixie cam through SPI, two servos through pulse width modulation, and then one laser driver also through pulse width modulation. Also, it's special in that it contains a main MCU and a network processor in one nice package, So that would lower the complexity when we print the PCB. Since our system has many intensive processes like image processing and network processes, we went with a divide and conquer strategy. So we offload all the target identification to the PixieCam, and the network processes are handled by the integrated network processor on the CC3200. And they communicate the results all back to the main MCU. So software. So in our software, we have 4 threads, starting with the highest priority, the watchdog, in case our system crashes, it will reboot, followed by the SimpleLink API provided by Texas Instruments, then targeting, and finally the WebSocket server. These 4 threads are managed by the free RTOS, real-time operating system, and they're initialized after our main thread has finished initializing. Here's our software state diagram. You can see our 3 main computational threads. We have the SimpleLink thread, which handles the TCP IP stack, followed by the web server, and then finally we have the targeting thread. So network design. So when we were approaching networks, we had to keep in mind that intensive processes like Wi-Fi protocols, SSL, TCP IP stack, we wanted to keep those off the main MCU, free up as much resources as possible. We also wanted to secure our network through WPA to keep unauthorized users from accessing our system. And also, to save time, we decided to make one HTTP web application. That way, instead of making a special application for each platform, as long as the platform has a web browser, which most of them do, they can access our interface. The web architecture. So in hardware, we have the CC3200, which connects to a 2.4 gigahertz antenna and broadcasts a Wi-Fi network. And then in the software, the main MCU will have a web server and event handler running, and it will communicate with the network hardware components through the SimpleLink API. Also, it's important to note that we're using multicast DNS and DHCP for name resolution and IP address assignment. The SimpleLink thread. The SimpleLink thread basically provides an interface for us to communicate with the network hardware components. The server thread is the one that basically communicates with the SimpleLink thread. It sends messages which are queued up in the SimpleLink thread, and then we can receive events from the network back as callbacks. SimpleLink thread is capable of running the full TCP IP stack, including an embedded HTTP server, but you'll see in a little bit why we couldn't use that. So network server. So originally we had used the internal server that's already programmed onto the CC3200, and we communicated by doing HTTP posts and GETs. But that was too slow and it had a lot of overhead. So instead we looked at making WebSockets. However, the included web server doesn't support WebSockets. So we decided to just make our own. Right? So after the transport layer, we reroute the TCP packets to our custom WebSocket server. So in our WebSocket server, first we listen for new connections. Right? After we have completed the TCP handshake, we process the HTTP GET request and serve up web pages stored on the SPI flash. Afterwards, we complete the WebSocket handshake and upgrade the connection to a WebSocket connection and process messages as binary messages. As you can see, the old method we did it was getting transaction times of 163 milliseconds. And after switching to our custom web server, we're getting transaction times of around 57 milliseconds. So in the network user interface, we wanted to show the user the current information of the system, so like target info, the current orientation of the turret, and its power level. We also wanted to be able to send information back to the system, such as power level, target range, some configuration information, and operation mode. Here in these pictures, you can see we have our Wi-Fi network with WPA2 security, and we've been assigned an IP address from the DHCP, and we were able to set our domain name too, to airstrike.net. The network user interface, we wanted to take advantage of HTML5, so we used WebGL to render the scene in 3D, which shows the turret, WebSockets for fast communication, and Canvas objects for animated 2D diagrams. are on the side over here. We felt that a 3D interface would be more intuitive to the user.
All right, the vision system. So we chose Pixie, which is a CMU Cam 5. They're made by Charmed Labs, and the reason we chose this is because, as you can see, it's built-in image processing. That makes things a lot easier for us in that it detects the objects for us, which means that the MCU has a lot less work to do. It detects it just does color blobs, and it gives us sort of center coordinates. So we program the colors we want it to look for, and then it finds them, and we can do tracking with that. It can support all those communication methods, which are pretty standard, SPI, UR, I2C. It has 75 degrees horizontal azimuthal view kind of thing, 47 degrees elevational view, and it processes about 50 frames a second. So to communicate with Pixie, we chose SPI, again, because it's faster than the other methods in a general sense. This also gives us a benefit because it's big Endian in SPI. Pixie uses little Endian otherwise because it does 8-bit words normally, but when we're in SPI, it does 16-bit words, which allows us to be big Endian, which makes us a lot happier. We don't have to worry about swapping bytes. It sends data again every 20 milliseconds. It's a 50 frames per second thing. And every frame is separated by 2 sync bits. This is sort of the message that we get. You get 1 sync bit that tells you you're on a new target, a new detection. 2 sync bits tells you you're at a new frame. So that way you know that you started over and you know you're detecting the same objects again. And again, it's just you got a simple checksum. The signature tells you which color signature you're looking at. So, one for us is green at this point, and so on and so forth. Sensors and widths and heights. So the biggest part of the vision system is actually, aiming a gimbal with a camera that isn't on the gimbal and really not even, it's like 3 inches down and an inch forth and an inch that way. So first off, we kind of have to set up transformation. So we have to set up a coordinate system, and up there you see our defined coordinate system. You've got your Z in the up, Y goes this way, X is down our line of sight. So if the gimbal and camera at 0, 0, they're both pointing down the X axis. Pixie's line of sight is the red line. And of course, then that's our Cartesian coordinate frame, and then we use that to define a spherical coordinate frame as normally defined, where here we have theta being the angle from Z to your radial vector, and then X being on or phi being between Y and X to Y. So first we get pixels. We have to then convert these into an actual spherical line of sight. To do that, we first take care of radial distortions using these 3 formulas, and we'll discuss that a bit more on the next page, because that was actually last minute. We discovered this issue very short notice. But normally what you would do is you have your total amount of degrees in a certain view. For instance, horizontal, we have 75 degrees of view, and then we also know we have 320 pixels in that view. And you just do a basic division to get your degrees per pixel, multiply that by your current center, and there you have it. You have your theta and phi. So you know your radial spherical coordinate. From there, you just convert to Cartesian using well-known formulas. This is nothing too special, but a little intensive sometimes, lots of trigonometry. Then you have to add your vector. This is where the actual distance between the two takes place. You have to factor in the fact that they're not looking from the same starting point. The hardest actual part about this is really measuring it. You have to be decently precise in order to still get center, and when things move a little bit, sometimes that gets a little off, and you just have to make sure everything's still adjusted properly.
Close. So, is this a 2D image? So how do you get?
Yes, the image. Range.
Yeah.
Originally, we were going to have 2 cameras to calculate it.
Yeah.
Unfortunately, now the user has to sort of define it using the web interface. We are set for 10 because that's what we decided on, and usually there's enough leniency that you can go back and forth without too much issue. But it is a user-defined parameter.
10 feet.
Excuse me. Yes, we work in the US units here.
And then, just curious, so I understand what's going on. So then, the MCU computes these.
Yes, on the fly.
Transcendental functionality.
Oh, well, which
Sign
function?
codes? Like, this is like a high-level language, or do you?
Oh no, we
provide
implement
algorithms
these
for this?
exact formulas directly in. We don't use any sort
Is
of
that a
function.
lookup table, or how does it?
It calculates it. Okay, so we know
But
these
I mean,
formulas,
yeah, I
we
know
just plug in the
calculate.
values. The only values that are given to us, we calculated K and K2 ahead of time, and these 2 values we know ahead of time. Everything else is on the fly. Well, this is also ahead of time. This is our position vector difference between the 2. Those are all ahead of time, and this is adjustable by the user, and so is range through the web.
But you have a math library access.
Yes,
That's
we
the
do.
way of
We like,
asking.
yeah, we say sign. We say sign, but we don't say give me Cartesian kind of thing. So
Thank you.
high level, but not super high level, as cool as we'd like it to be. But anyways. So once we do that, we have our Cartesian line of sight from gimbal to target, and then from there we just again convert it right back to spherical. This does cause some inaccuracies. We're using floating points, so we're not using doubles for memory reasons. So you lose a little bit of accuracy when you're dealing with these functions, but fortunately we don't go near any of the defined points that cause singularities. We don't have that kind of range, so we don't have to worry about them. So this was something that we learned when we tried to take our thing to the extremes. We tried to take our balloon to the edges of our camera, and we noticed it was always off. And for the longest time, I thought it was a vector issue. I wasn't actually getting the distance right, so we were constantly remeasuring. Finally, Scott actually says, well, have you looked at the distortion? So we came in, and Kevin had actually done this before at work, so it was really lucky. We were able to, you take a picture of a checkerboard, and there's an application in OpenCV that uses the Braun-Conradi model in order to kind of calculate your distortion on a radial using, which again, these formulas that we used on the last page. So you calculate these two coefficients, you plug them right in, and it gives you, you give it the pixel, and it gives you what pixel you're actually kind of looking at, if everything was perfect. And this would give you, if you had an image like this, it gives you this image kind of thing.
So those diagrams are from your PixieCam?
No, well, this was taken with PixieCam.
Oh.
These two are, well, no, this was taken with PixieCam. This is what gets spat out when you do the radial transformation on OpenCV. Like, we took these pictures with PixieCam, sent them to OpenCV outside of our system. This is all done outside our system. And then it did the math for us to give us these numbers that we could then, they're
This
constants.
is on your platform, so it's very visible. This is an issue.
Yes, it was a
These are
very
not like
visible-
from a web
No, this
interface,
was,
right?
we noticed really quickly, we looked at it, we could see the roof was curving, and we noticed at that point it was a really big issue that needed to be solved.
PixieCam needs some work.
It needs a lens that doesn't curve as bad, yes, I
No,
agree, but then we might lose
actually-
field of view.
Actually, most cameras use DSP to correct. The lenses are distorted.
Yeah, learn some.
The images are distorted. They use DSP to correct. Most of them are like that. Unless you buy the expensive DS.
So Pixie
DSLR.
as a system is only $80, so the
Oh, yeah.
camera
Very
probably is one of the
expensive.
least expensive parts of it. It's mostly the processor and whatnot. So yeah, it does have really bad distortion, but fortunately we were able to correct that, and the accuracy was a lot better afterwards. So last thing is we're going to go through the targeting thread. Pixie is again a simple detector. It doesn't track. Instead, we define our tracks. Basically, Pixie, we take the first thing Pixie gives us, which is always the largest object of the first color signature. So like I said, our first one was 1 is green. So it finds the biggest green balloon first, and it says, okay, that is my target. And it will do its best to follow it. Whenever it does a new detect, it looks for the closest object to where it last saw its primary target, and then updates its information. We have tolerances defined in our code, which can be changed on compile, but and those are they're percentage tolerances of a radial difference. So like if you're so many percentage off from where you last were, it says okay, it must be a different balloon, or I've lost it. My information doesn't match with this, so therefore I have to treat it as a different balloon anyways, in order to not have bad formula and therefore end up way off target. So it takes care of that. If no object is found within the tolerance, it just picks the next biggest balloon, or actually the biggest balloon again. It doesn't bother searching, it chooses the best balloon and goes with it. But we do wait a couple frames. We're not instantly switching balloons. We wait a couple frames to be sure that we've actually lost a target and it wasn't like the Pixie hiccup, because Pixie does sometimes not perfectly 20 milliseconds. We keep count of the number of frames we've had that have had a viable balloon pickup, so that we know sort of confidence of how likely we are to be hitting a balloon with our laser. We do calculate velocity, but unfortunately our servos only run at 50 hertz as well, so they run at the same speed as our camera, which means by the time they've moved to the new coordinate, we've already picked up the next target, so it doesn't really help too much. We also don't have accurate timing information because we're going off of the MCU, which doesn't have a real clock. It has its built-in clock, and so it's been a bit difficult to do proper velocity. It does a little bit where it detects where it thinks it will be when the servos next pick up their cycle, but again, it's still a little off. So it's mostly it points where it is and tries to follow it, and we'll show you a little bit how that's kind of been an issue.
Okay, so for the PCB design, we have 2 different circuit boards in our actual system. So to begin with, we'll work with the PCB that contains the MCU itself. So the CC3200 is a 64-pin QFN chip, and this is the schematic for the actual CC3200. Up here in the top right corner, this is all the networking portion for the chip. This is where our 2.4 gigahertz antenna is, so that we can broadcast our signal. Also, a couple different filters in order to make sure we only are operating in that actual frequency. Down here, the CC3200 uses 2 different clocks. The first one is a slow clock, operating at 32.768 kilohertz, and this is for real-time processing. And then in order to do all of our image processing and networking processing, it also operates with a 40 megahertz crystal, and this is all for the internal processing of the chip. Located here on the side are all the GPIO ports. I'll go into how these are broken out later on in the presentation, but basically this is where all of our SPI ports that we connect the cameras to go to. In order to flash the code to the board, we use an FT2232D debugger chip. Over here in the top left is our micro USB input. We can either power the entire board with this USB port, and it'll have a 5-volt input. We don't do this for the actual system because we connect it to our other PCB for the power, but this is how we're able to power the board and get the code onto it as well. Because the input from a micro USB port is 5 volts, and a lot of the parts on the chip or on the board itself operate at 3.3 volts, we use a simple TPS voltage regulator to drop the voltage from 5 to 3.3. That way we don't fry out any chips on board. And we are able to still use both the 5 and the 3.3 volts as well. So this is how the GPIO ports are broken out into. We have 2 20-pin headers located on the sides of the boards. And as you can see, several different words are changed. These are the ones that we actually changed and make sure that we directly routed them to certain chips or certain pins, instead of going through other circuitry. So as you can see right here, this is where our current driver PWM signal comes from, and servo PWMs, and our SPI clock and whatnot as well. This is the board layout that we designed. It's a 4-layer board. The top layer is this bright green color. The second layer is the ground layer. The third is this dark green, it might be hard to see, and then the bottom layer is this yellow. And we use the Cadence package for this PCB because most of TI products I found, all their reference designs and their forums talk about Cadence. So the schematics were done in OrCAD schematic capture, and then the PCB design was done in PCB editor as well.
Okay, so the directed energy.
One quick question, did you do any simulation before you went to the 4-layer? Because that's very great.
Well, we were able to do some of the simulations. The majority of the design was, the majority.
It's a question.
Right. The majority of the design was based right out of the data sheet for the CC3200 and then the debugger chip. All we really had to do was make sure the voltages were correct going to the GPIO ports.
So what, just so I think I understood correctly, what course did you know enough to be able to do that? Just your own?
YouTube.
YouTube?
Yeah. Basically, I've never done any PCB design, and basically through the forums.
Embedded systems.
So you use OrCAD to.
Yeah, I used OrCAD for the
to-
schematic.
We took embedded systems, well, you know, they don't get that far.
Yeah, this is probably the very first time they've been asking us to do
Yeah.
And so
And
there's
it's a 4-layer, so how do you do the embedded one? I mean, the one of the embedded one is the ground, so that's okay. But the third one is still embedded. How
Right.
do you do that one?
Well, most of the chips on the board are actually surface mount, so it doesn't interfere. We don't drill holes all the way through. So certain parts, obviously, the pins go all the way through, and we have vias going to the top and bottom layers. But using the surface mount chips, we were able to not interfere with the middle layers.
No, but how did you cut the?
Oh, no, oh, we don't
they have it
manufacture it.
manufactured.
No,
Yeah, we don't
manufacture
manufacture
it,
it.
and then they.
Yeah.
Yeah, who did you use to?
Oh, I'm sorry. For that one, we used 4PCB because
Okay.
they didn't limit the size of the board.
Yeah.
So because there were a lot of parts, I didn't bother with the size. So for that board itself, 4PCB.com, they say all four layered boards are $66.
That's the student price, though.
Yeah.
Right.
Did it really work?
Well, we'll get into that.
Oh.
Okay, so directed energy system. So when we were first brainstorming on the directed energy system, we first thought we could use like Fabry prototype resonator cavity to generate our laser energy. But that would actually prove to be too bulky and very expensive and eat up our whole budget pretty much for the system. So the next best option, probably the best option, is the laser diodes. For the visible regime, we could choose anywhere from 405 nanometers up to 808 nanometer wavelengths, and we ended up going with blue light, which sits at 405 nanometers, and we'll explain later why 808 might have been a better choice. But we had two separate laser diodes we tried. One was a single mode output, the other one was a multimodal output. As you can see from this plot, over a larger propagation distance, a single mode beam would actually suit us better for distance, so that's why we went with that. The diode we chose was the SO6J diode, and we drove at 450 milliamps, and it had an power output of about 625 milliwatts. We first experimented with two separate lens systems. One was just a standard 3-element glass lens, and as you can see from this plot, that only gave us about just over 400 milliwatts of power. Then we switched to a G2 anti-reflective coating lens, and that milked out almost another 200 milliwatts of power, so that proved to be very useful. So yeah, the collimating optics is a big part of our laser diode system because the light emitted from the diode is highly divergent. So we had a lens that would collect all the energy, and we could focus it out to our targets to burst the balloons. Another thing to consider when you have a laser diode is the thermal energy generated from it. So our heat sinking material, we chose copper because it has a high thermal conductivity. And our heat sink, rather than being a block like that, we included fins on it to dissipate the heat into air and keep it as full as possible. Yeah. The power delivery. When a laser diode when a voltage source is applied to a laser diode, they eat current, and they eat so much to the point where they'll just blow themselves. So we need a way to regulate that current to the laser diodes. So to do so, we bought the FlexMod P3 laser current driver. We chose this one because it has a modulation input, so we could tune the power output we wanted from the MCU. So we have two operating laser modes. One is the low power mode where it outputs 10 amps, giving us less than 10 milliwatts of power, so the laser operates like a LED. And then the high power mode, to be safe, we set at 450 milliamps. We don't want to push the diode because they're sensitive and delicate, so we learned that the hard way. So that's our high range, and the power is adjustable anywhere in between that range. Now, to align us with the targets, we have a 2-axis gimbal system. Originally, these gimbals were used for little mini HD cameras, but we modified it to fit our laser diode and the heat sinking assembly. And due to the added weight of the heat sink, we decided to go with metal gear servos for the higher torque values over a standard nylon servo. And so yeah, that'll compensate for the additional heat. And these are the specs of the servos. There we go.
So for the second board on in our system, we use it basically just to regulate the voltage going to all the different subsystems. Fortunately, the majority or all of the subsystems operate at 5 volts, so we were able to use a simple barrel input that'll convert a wall or a wall input straight AC to DC, and then drop the voltage down to 5 volts as well. And we connected it straight to this 10-pin header. 7 of the 10 are connected directly to the barrel input. The other 3 go through this circuitry, which is basically, we have the input from the PWM signals from the MCU coming in at 3.3 volts, and we use PWM for both servos and the current driver. So we need to bump this up to 5 volts in order for them to read the signals correctly. So we go through another voltage regulator in the opposite direction, and we drop the voltage down to 3.3 volts, and then through this transistor circuit, which we have 3 of them, but I'm only showing 1 because they're all the same. We have the input from the MCU at 3.3 volts, and then we have an input from the voltage regulator at 3.3 volts, and it acts as a switch. So once it sees the voltage, it opens up, and then 5 volts is able to go straight to the other 3 connections to the headers. So then those all 3 operate at the 5 volts, or excuse me, all 10 operate at 5 volts and go straight to the devices. The bottom one over here with 5 pins, those connect straight to ground. That way we have a common ground between the MCU and the power board. And then the top 4-pin header is where we get the signals from the MCU itself.
Just so I can learn something, because
Yes.
I don't do the power supply design work. What is barrel?
Um,
Another word.
It's just the shape of the input. You might be able to see it. We could pull it out later if we want, but
No, you can't put it on the
Where's the
laptop.
AC?
Oh, it's actually in the cord. So what you plug into the wall, it converts all of it in there.
I have to learn it.
Well, I'll show it to you once.
Nice little PowerPoint that's going in.
Once we're done with the demo, I'll be happy to unplug it and show you. It's just the barrel is the shape, so that's what we call it.
You've probably seen them
Transformer, or what is
before.
it?
It's like
What
the
is that?
plug into
I'm just.
Can your thing run on battery?
What is the physics?
It's this.
Yeah.
This is a barrel jack. You
Barrel
plug it into the
jack.
regular. Yeah. You just it's like how you plug in a laptop. It's the same technology.
It's already DC though.
Yeah. Okay.
It
Okay.
converts
No,
it to DC.
It converts it to DC inside the.
I'll ask offline.
Okay.
It's coming from a wall work.
Yeah.
It goes AC to semi-regulated DC, and that's what goes into the software.
Okay, then that's making more sense, okay. Thank you, good.
And then this is the board layout. It's a small 2-layer board, and I decided to use Eagle for this one. That way I had experience in both Eagle and Cadence in case I needed it in the future. And I printed these out at Osh Park because Osh Park, their pricing is based on the size of the board. So because this one was significantly smaller, then it was cheaper that way as well. So our administrative content. As you can see, we have several different subsystems, all various areas of expertise, I guess. So we were basically split up, and Kevin and Chris basically handle all the software, with Chris handling the camera and Kevin working with the networking. Andrew worked mostly with the lasers and the gimbal and servos, and then I worked with the PCB and power. And then because Andrew and I were working with the majority of the hardware, the two of us kind of worked together trying to come up with concepts for the housing itself. Here's our budget distribution. We were funded, fortunately, from Boeing, and we received $900 from them. And after all of our components and burning through different components, we still managed to remain under our budget.
This does include the failed things that we had to buy again.
See, but that's learning to me. I think if you don't burn up a few chips, then.
Well, fortunately, we only burned
You
one
didn't
ship.
learn.
We burned 4. Well, we'll get.
Well, too many is not good too, but.
No. So, some of our issues. So for the MCU PCB, the first one we designed, the power distribution worked perfectly. The board was getting either 5 or 3-point volts depending on what it was supposed to. The LEDs indicating the power worked correctly. And we believe the MCU was working correctly. It was sending signals that would be normally flashed onto the code itself, or onto the chip itself. However, we believe we ended up burning out either the debugging chip, or there was a short somewhere in one of the middle layers that I couldn't access, which would be from the manufacturer itself. Because when we would plug it into the computer, it doesn't read it. And I was able to pull off one of the chips straight off of a separate TI launch pad and put it directly onto mine that we knew that worked. And unfortunately, it still didn't read it. So I have a feeling there was either a short in the soldering or in the trace itself.
Alright, other issues we had. So originally, like I said, we were going to use 2 cameras. And the only reason we didn't is after 2 weeks of dealing with the CC3200 and its rather finicky SPI, we couldn't get that to work. Originally, the Chiba C it did, but we did switch chips in order to be more conservative with our PCB. So that is the main reason why we went down to 1. So that was one of our biggest issues. We spent a lot of time trying to get through that. Fortunately, the tracking actually still worked rather well with 1 camera. And even when you, like I said, you have to input a range. But even when you're off that range, like you can say 10 feet and come in at 5, it's still pretty solid. And even, you know, you can say 100 and back here, it still pretty much tracks it right on. So it doesn't seem as vital as one might think at first. Another issue we had is the laser diode turned out, so this is what Andrew was saying, why we might have wanted to gone with an 808 nanometer because it's actually pretty much invisible to the camera. One of our issues was is ours is very bright and purple. And so when you aim it at a balloon, trying to pop it, it colors the balloon purple. Pixie then doesn't know where the balloon is and immediately turns off the laser and tries to find it again, which causes it to turn the laser back on, and it has a little bit of an issue there. Fortunately, most balloons pop way before that happens. Sometimes they don't. Sometimes they don't pop. That usually depends on the color of the balloon, if they're moving too much, or if they say happy birthday on them. Because happy birthday is written in white, and white doesn't absorb the laser very well. Otherwise, we have, like I said, the velocity had some issues due to the slow rate of the servos and the fact that we don't have a real clock. An improvement to that would probably be if you can get like an atomic clock chip or something to hook in and give us real-time data somehow that we can access on the fly. I don't really know how that would work, but that would probably have been nice to have, just to give us proper velocity measurements so we know how much time it would take for the balloon to move. That's just that. But also just getting faster servos. These servos are meant for more like moving a robot driving or something, I guess, or aiming a camera kind of doesn't need to be right on perfectly, doesn't have to really follow it really fast. All we know is the velocity is a little finicky.
Yeah, also since we implemented a custom web server that runs on the main MCU, we couldn't take full advantage of the network processor. So that means we cut into our main resources. And so that means the threads aren't as fast, and to account for that, we limited ourselves to one active connection to conserve resources.
And our last major issue was burning through our laser diodes. In total, we've gone through about, let's say, four of them. The first one blew under our first set of testing. That one was understandable. We're like, all right, we'll just get a new one. Just yesterday, another one blew while we were testing low power output. So we ran to Walmart to buy little red laser pointer ones, and we ripped that open and just soldered on some wires and modified that to fit in our system. While testing, we actually blew one of those.
But fortunately, the one that blew yesterday was after we recorded video with our high
So
power
we do have
laser.
proof of the high power laser functionality. It's just that data doesn't work anymore. We killed it the next time we were changing this.
So this concludes our presentation. Thank you again for coming and taking time out of your busy schedules. Is there any questions?
So networking is to provide the interface, or are these components networked somehow?
Networking is just to provide an interface from
got
the
it.
web browser to our MCU.
And for our demonstration, we have several videos that we recorded down in the Creole lab with the high power laser. And then once the videos are completed, then we'll have the demonstration here and we'll be able to show the networking.
Yeah, the CC3200 is a Wi-Fi transceiver with an ARM Cortex M4.
Cortex and Pro.
Yeah, integrated into one piece of silicon, one part.
So your system works only if the target is in the view of the camera.
Yeah.
The camera itself doesn't track.
The camera does not move.
It's
Yes,
only
it is a solid.
the laser is on servo. but-
Yes, we didn't want to boresight the camera for a lot of reasons. Safety, one of them, because now it can't go outside of a certain amount of range. And also because I thought it would be more difficult, actually, to keep the camera off, because then I have to deal with more transforms. I thought it'd be a better learning experience for me in the long run.
Of course, you could use one of those anamorphic lenses and get a 180 degree
Very cool.
tilt and then
We
transform
already
it
have
back.
radio distortion, I don't want more.
Okay, is it ready to begin the demo? Okay.
All right, you start the videos. I'm going to make sure this is running.
All right, so I have printed out
Where
test
glasses
receipts.
are in?
No,
Yeah,
this is
no,
a
this
laser.
is
Well,
oh, no,
the
no.
real one we did, this was a laser pointer. It's as
Yeah.
dangerous
This
as
is
this.
Yeah. So thank you for.
Just making sure.
Yeah. So because we had to do a lot of the demo outside of the room, I printed out test procedures going over what each experiment is used for.
Thank you.
Sorry.
What's the total runtime of the videos?
It's
That's
probably
a good
about
question.
5 minutes with talking. It's not very long. Okay, so this is actually a picture of our laser diode and the beam. Just that was our picture. I thought it was kind of cool, so we put it in. So our first trial, we replaced the heatsink in the gimbal itself and put in this little camera in it, and we were able to track. So what you see is exactly what the laser would see. Now, of course, the angling is slightly off because the lenses are in different locations, but you're able to see exactly what Pixie sees and what it would be technically shooting at.
And also you'll notice at times when he goes too high, it will not follow it or it'll move to 0, 0, which is program behavior. It's outside the Pixie's range of view, so you won't be able to track it anymore.
Right. We wanted to show the limits of the field of view itself. So that's when it went too high out of the field of view.
When Pixie loses its target, it's programmed to go to 0, 0 and shut off its laser.
I was wondering where I jumped this one.
Yes.
And this is 10 feet is roughly at the end of this back table, so this is a little closer. We were just doing that so that way we didn't have to keep trading sides on the table. But we will be testing it at further than the minimum range that we put in our requirements.
And there you saw that stuttering. That was what I was talking about, how the gimbals only run at 20 milliseconds. If I command it, at the end of its 20 milliseconds high output, it says, oh, I have a new area to go to. So it does that stutter issue.
It still works pretty good.
Yes.
So for the second trial, we shut off the servos because we didn't want it moving, and we told Pixie to track to a red balloon color. This video is very quick. We wanted to show how fast it would actually pop it, and then we'll play it in slow motion. That way you can actually see the laser itself and how quickly it turns on, and then how quickly it turns off once the balloon is popped.
sound, guys?
I hear it on this.
Anticlimactic.
Or whatever. Yeah.
Maybe not, no, no.
Is it?
The VGA cable's not
Oh,
finished.
there it goes.
So yeah, the laser is programmed to turn off once it doesn't see a target or once the target's popped, and while it's moving to the second. So from that video, you can really see.
That's up the pan on the wall, or?
No.
No, it
No,
was
no,
fine.
no.
We had some moments where it ran along the wall for, when we were testing it, it never hurt the wall.
Yeah.
It hurt other things that we put in front of it, but not the wall. A Pringles can that smoked a little bit, but that's not it.
All right, trial 3. So for this one, we told it to attract to green balloons.
Those are green, I know they look a little yellow in this video, but.
So we wanted to see how Pixie and the camera and the laser would react when there was multiple objects of the same color. So what we expected it to do was the balloon on the right is larger than this balloon right here. So Pixie should go after that one first. Once that one's popped, it should turn off the laser, move over to the second one, and then shoot the laser at that one.
So this is where I talk about the happy birthday issue.
Oh, yeah.
It keeps hitting the light and it's not actually being able to pop it. And also the laser's so bright it does lose track of it. As you can see with the other one, that's normally not an issue with that color. So it's purely the rotation of the balloon, and at this point there's not much we can do about that except use balloons that are a solid color.
What was the difference in depth between the first balloon and the
Probably
second
about 2
balloon?
feet.
Yeah.
About 2 feet, okay.
Yeah.
Not much.
We also think it, as you can see, when it flashes like that, it just means that it sees the target,
And
we shoot the laser, changes the color, oh, it doesn't see it anymore and turns it
Again,
off.
safety was a priority, so we wanted to make sure that thing turned off whenever it didn't see a target anymore. So.
So for this trial, we're able to exactly show what we were talking about when it would turn on and turn off, except for this trial, we wanted to put it where you could see the happy birthdays, and instead of it popping one and then going to the second one and turning on and off, you'll see exactly how it trades between the
And
two.
these balloons were not these ones didn't pop out of relation, so it's more like a visual demonstration.
Right.
And so you see the jumping. This is what I was talking about, where it'll lay on it for a while sometimes, but it does have that issue where it suddenly doesn't find it, and it is a little misaligned in this. That's why it's a little off center. We have to. This is when we were even less recognized, and we had to deal with the fact that sometimes things move when the servo moves really fast. So a few of these videos are off center, but the ones that are on center are when we have it aligned. You'll see that here because we have it fairly well aligned for this system.
And if we added a filter to the camera to filter out the color of the laser, then we believe we wouldn't have this issue.
The problem is we're worried about filtering out the other colors and not getting the balloon. So it would be an addendum. We would try to do that if we had more time and resources.
So
Now,
for-
this one was done with, purposely with low intensity laser,
Right.
Just for demonstration of that.
Right. So for this trial, Pixie's actually able to put primary colors, and it says, okay, if it doesn't see a color of this specific one, then we'll jump to another
That's
one.
the signatures I was talking about earlier. We define, it has a list of about 7 colors to look for. The first one is one to look for first, then second, then third. So in this one we had blue first, green second, which is actually yellow in this video, the projector, and then orange third. And you'll see how it behaves when it gets that. And this is that happy birthday-ish issue. And actually, no, that was just this color balloon. It was spinning, I think, at this point, and that might have been causing it. We're not entirely sure. It could also be the color of the balloon and the just the angle. But it did hit that happy birthday a lot, and just wasn't able to maintain a constant on it. So this is, again, one of the issues we have with our system and moving balloons.
But it shows the proof of concept where we could target the blue, it shot it, saw that it was gone, went to the green, burst that balloon, went back to blue because it saw it was primary over the orange, tried shooting it, and then went to the orange and then finished off at the blue one.
And this is with any laser system, you're going to find certain colors that don't pop as easily. That's just because that's how light absorption works.
So for this trial, we once again went to green balloons, and once we popped this balloon, then we wanted to release one to see how well it could track a moving target and see if it was able to pop that one as well. Now I'm out of the field of view of the camera, so there's no harm of the laser shooting at me.
And as you can see, it always manages to hit on the balloon until it goes out of sight. Unfortunately, it wasn't long enough or strong enough to immediately pop it. Again, this could be movement, so it doesn't always hit the same point, or it could be just the color. Well, obviously not the color in this case, but it could be a whole lot of things. But yeah.
But as you can see, when that one was moving up, the laser was right in the middle of the balloon every time. So the tracking and the servos are able to follow it. It's just the fact that the laser is so bright on certain balloons, whether even though they're the same color, That one actually, I believe the Happy Birthday was facing forward, so it was different colors that it was seeing.
And again, if you move, you lose the exact skin you're looking at, so the heat is dispersed over the balloon rather than pinpointed for as long.
Yeah, and also the level of inflation. Did you inflate them to the
We
same
always
all
tried
the
to go
time?
to a similar level where it was, you had enough color to still.
I'm thinking
what the laser went
the
across.
thickness of the
Yes.
the material.
It could also be an issue. These were not perfectly inflated at the same level, so that is an
Because
issue.
I mean, you build up more pressure, it stretches thinner,
There
takes
are
less
two ways to
energy
do
to,
it, yeah, there are two things you have to worry about though, because if you get too thin, then the laser just passes through, it becomes more clear, so you have to be
Yeah.
careful to balance that, and, I think you would have been close about that.
Yeah.
So it's a balancing act, and
Okay.
sometimes it's not well balanced, and that's where you see balloons that don't go.
So for this one, it's the exact same as the last one, but we wanted to try it with a different color to see how it would react, so we're using yellow this time.
So once it's stabilized, give it a second.
So yeah, the balloon is rotating. And
So I think it is also just not sitting at the same point long enough, which is
Or
expected.
increase the power of the laser.
The
Yeah,
way
we didn't
around
wanna
it
burn out the
we didn't want to burn out the
laser, yeah.
diode. The way around that would be getting an even stronger diode and push
Yeah.
out, like 2 watts of power. It'd blow it up, just don't hit yourself.
So for this time, we attracted to green balloons again, and we added a little more weight to the string. That way it didn't float so quickly to see how it would react.
Sort of thing. Noted it.
So once again, it's staying right in the middle every time, but with the rotation and the movement, unfortunately, it doesn't see the balloon anymore once you fire it. But we were able to put it in front at a much closer depth, and it pops it instantly.
Yeah, and you can see there Pixie moving on the side again at 0, 0. Once it loses the target, it's meant to be safe. It works very hard to not hurt people.
So this video is probably the best one that we have. We attract to a yellow balloon this time, and instead of just releasing it, we throw the balloon. That way, there's no prediction of where it goes because of the weight distribution. It rattles everywhere besides just going straight up.
But we still.
And fortunately for this one,
Now you
it's
see
able to
that-
pop that one when it's moving.
Oh yeah, slow motion missile trails probably really playing on attack. We were off center at this. We were not aligned at this point. But
And right now it gets out of the field of view, which is why the laser's turned off. Not that it doesn't see it because of the color or anything, it's just too high and we're too close. And then you also see the laser pointed
It
on the
actually
wall. It's
reflects
passing
off the
through-
side
yeah,
of the balloon.
It's passing through the balloon on the side of it. It's not that it's missing it. It's just when it's on the corner of it, and then it'll reflect
and
to
then
the
you
side
see it
as well.
fly back with the momentum of the explosion.
All
Very
right,
fun.
so still. And then for the last trial, we
We were just
turned
testing
off the
laser
servos,
itself.
turned off the camera. We didn't want to attract anything. We just wanted to turn the laser on full power,
And show
turn
the
off all the
behavior.
lights, and see how quickly it would pop everything
And the
in a
behavior with
line.
different colors of balloons.
Right.
So you'll see. Lights go on.
This is actually when we took that picture earlier.
And that balloon will not pop due to it's basically white. It's high, it's very light pink, so it'll hold that. And then we came in real quick, and it might be a little dangerous, but let's see, Scott instantly pops the other one. So it gives you an idea of why color is a factor.
And then, just for fun, as you
We
could
didn't-
imagine, there was plenty of this. This was the ending of that one video.
Unfortunately,
Helium balloons are nice that they float, but unfortunately they go to the roof way too much.
we had to do a lot
Well,
of.
you had a laser, you could just shoot it down.
Yeah.
Well, we still wanted to use the balloons. We had a limited number of them.
So this concludes the video portion. Now we'll go into an actual demonstration where we'll have
You
balloons.
need the lights back on for that?
That's
It'd
up
be
to Chris.
best because that way Pixie doesn't have to change the light level. Yeah. That's adjustable.
Well, with the light number 2 on,
You have to switch on.
Yeah, I know what I do. It's an auto mode. Hold that balloon. So it's trying to turn the laser off. Unfortunately, we have the switch off. Laser has a separate switch.
For safety features, we didn't want it
And
firing
there's a 7
when we
second
weren't
interlock,
ready.
so give it a bit.
This is what
Okay,
Pixie is seeing, or?
This, yeah.
Okay.
Okay, so I'm gonna turn it on.
As you can see, it's holding onto its balloon. It's in the autonomous mode. We have different modes of operation. You can see the tracking issue we're talking about. It's a little slow behind it, even when you move kind of slow, but it still stays on that balloon.
Fortunately, the laser, I'll let you go ahead, but the laser is right in the middle and it passes through, so it might be a little weird to the eyes when you see it on the board, but it is going to be on the balloon as well.
The other one doesn't pass through, it just pops. So this one passes through. Different lasers. But as you can see, we have this little video here. Right now it thinks it's at 10 feet, and as you can see, that doesn't actually bother the sensor really at all. This is why I said range isn't too big of a deal. You're really probably about, what, 5, 6? It doesn't care. It gives you slight inaccuracy, but generally, unless you're right up close, it doesn't matter too much. You'll still be on the balloon. And you can kind of lift it elevation. You'll see it sees the bottom of the balloon still. If you go even higher, though, it gives up, turns off, goes straight to 0.
This is when it's out of
Yeah,
the
you
field
can
of
hear
view.
the servo just gave up.
It goes to 0, 0 because we want to make sure we have a known point where we'll point to and turn off this laser. It makes things simple. And then if it gets to the edge
So
of
this,
the field,
yeah, this is the edge of the field of view.
and I can get a secondary balloon and to color to prove the shifting that we were talking about.
You need kind of,
What? Hold that one down. So to change balloon colors, the way it works is you hold Pixie's little button here. It cycles through some colors, the colors to designate which target you're looking at. So now its secondary target is set to red.
So it's gonna stay on the green. Once I hide the balloon, it goes straight to the red, and once I bring it back, it comes straight back to where the primary color is.
And you can do that for up to 7 colors about. That's Pixie limitation. And yeah, if somebody has that hidden, it follows the red one. Perfect. And we can do a third too. I don't know if you want to. It's not really necessary, but it would demonstrate the same concept.
So Pixie is passed in the elevation, isn't it? For the
Yes.
two?
Pixie,
So
well,
that's
Pixie
the-
gives me pixel coordinates. I compute the
That
azimuth.
was the map.
Yes,
Yeah.
I compute the azimuth and elevation, deal with radio
Awesome.
distortions.
So then we're watching this over the web?
Yes, this is
Firefox.
entirely wireless. This is through a Firefox browser. We do have an issue with Android because Android doesn't have enter events, so when you try to enter in values, it doesn't. You can watch it, but it won't let you enter in values. You can still change the button and you can do the submit offset, but because it's just the way Android browsers work, and it would be a fix that wouldn't be too difficult. We just ran out of time. But if you hit enter, on a keyboard, you hit enter, we get an error event. If you enter on an Android, it doesn't actually send an event. It leaves a text box. So it doesn't tell the web browser that it's ready to take that value. It's just an issue with that browser.
So this is in autonomous mode where the laser will automatically turn on if Pixie sees a target. We also can move over to manual fire mode where it'll track it and no matter what, but the laser will turn off.
Yeah,
You
so
control
we
the
can
rate of
send it
laser.
to,
So it sets like
50.
50, and you actually can. It's a lower powered. It's hard to tell if this light. If you put it to like 10, it's more
It's okay,
obvious.
we see it.
Yeah.
Dimmer now. So you have full control over that range. You can make it pretty much really bright, really dim, and then
Yeah, and
How that works.
then we have manual full, which is
you get full control over the laser and the servos.
yeah, I can
So it's not going to
like-
track me anymore. We just command exactly where we want it to go.
Yep.
But you can see Pixie still sees the balloon correctly.
Yeah. Or if you hit that one, you'll still see this one. You get a nice balloon.
Yeah, once you go to autonomous on the topic.
It'll immediately aim for him, and yeah, you can still see the red one shows up now. We're back on autonomous.
Yeah.
Hide this one, it gives up. Pull that one back out, it finds it. Nice, clean, mostly not dangerous.
Fun.
Very fun. Everyone wanted to play this lab, like to bounce the
Yeah.
balloons around. Oh, because the green, you got in the way. The green one, you can't see the green one.
Anything you want to show them on the inside?
If you want to, we don't like opening it because it's not, again, ruggedized, but we can show you where everything is and how it hooks up.
yeah.
It
Are
doesn't
there
really matter.
any
If you don't
questions
expect,
before?
yeah, if you want to see more of this part, do it now because we will probably be missing one.
Exactly, I assumed that's where we were at.
We're nerds, we love this part.
All right.
Okay, well, we're ready.
Turn off the
Everything down.
switch.
Switch is
I
off.
only have about 3 minutes for that. 'cause we got
Just
next
give us
group
the,
in.
let me
Yeah.
see a little bit.
Okay,
and we'll be happy
let's
with it.
pull this cap off.
So yeah, we 3 layers. The top part can pop off. And
Oh,
then
you
the
guys
middle
are like packaging engineers.
Yeah, tell us about that. So there's where our switch
Yeah,
connects. This is where our gimbal comes in. Then it goes
This
down.
foam thing was a good idea too, because sometimes they get stuck in metal and a bunch of complicated stuff.
We want something
Idea.
that was lightweight because we knew
And
it would be
the only reason the
Move
foam's been an
quick.
issue is ruggedization. Otherwise, it's been
Yeah, but
really
that's not
useful.
what we're here for.
Exactly. And when you come under here, you gotta be a little careful here. Can you hand me the can someone give me the laser pointer and get them some light?
I don't have it.
You have it. Oh, your phone.
Your phone has a,
Oh yeah.
Now we got this one.
Flashlight?
Yeah, it's got a flashlight. So you come in here.
Just the basics, let's just see what's going on in here.
You've got your
Okay.
current driver over there.
Okay.
It's the current driver. That's the power board, which is a little up. And then there's our MCU. We actually didn't mention this is a battery. It's needed to help the current driver because it operates at 7 volts or 8 volts. 9 volts. We're currently operating at 9,
between 7 and
but
Okay.
it's 6 to 24 volt operation. It does not really drain that battery on this mode, but with a real laser, we could go through batteries in like 10 minutes.
Yeah,
so.
it goes quick. Gone through a lot.
But yeah.
Okay,
And this is
well,
fixed
thank you,
knowledge,
graduation. Good job.
Thank you, guys. Thank you.
And I'll unhook it and I'll show you exactly what I was talking about with the conversion.
Okay, guys.
While you're cleaning up, I'm gonna let the next group come in.
Go
Yep.
ahead.
Good job.
Again, my brain.
So how can we have you come back for grad school?
Me?
Anybody
Oh.
in this group.
Amy more than one.
Hey, Foxy, how are you doing?
How's everything?
Good.
You missed so much fun. We were shooting balloons.
I tell you, I'm trying to commit even more, but it didn't work.
Do you want to show the barrel?
Oh yeah, do you want to see that barrel jack still? Or do you